Hello everyone, and welcome to Jam Academy. In this very short lesson, we will talk about the mathematical definition of work. In other words, I'm going to show you how to calculate the work done by a force on a system. By definition, work done is the mechanical transfer of energy from one object to another. That's the meaning of the word work. But how can we calculate the work done by an object? Work is done when a force moves its point of application along its line of action. Let me say that again. Work is done when a force moves its point of application along its line of action. In other words, if there is no displacement of the point of application of the force, then no work is done. Mathematically, the work done by a force is given by the product of the component of that force in the direction of displacement and the magnitude of the displacement of the point of application of the force. In other words, the work done by the force f of x is equal to the component of that force in the direction of motion multiplied by the magnitude of the displacement of the point of application of the force. But the question is, what if the force is not in the direction of motion of the object? If that is the case, then we can see that the work done is equal to the component of the force in the direction of motion multiplied by the displacement. So this is equal to F cosine theta multiplied by delta x. In other words, W is equal to F delta x, the cosine of theta. Now the angle theta is the angle between the force and the displacement vector. The angle theta is the angle between the force and the displacement vector. So the next important question that I would like to ask you is, what then is the SI unit for work? Remember, the definition of work is the mechanical transfer of energy when a force moves its point of application along its line of action. In other words, the unit of work is simply the unit of energy. And if energy is measured in joules, it means that work is also measured in joules. What I mean by that is, work is measured in joules. That means that 1 joule is equal to 1 Newton, which is the unit for force, multiplied by meter, which is the unit for displacement. If I want to express this in base units, remember that 1 Newton is equal to 1 kilograms meter per second squared. So this implies that 1 joule is going to be equal to the kilograms multiplied by meters per second squared multiplied by meters. So if we further simplify, this would mean that this is equal to 1 kilogram meters squared per second squared. So this implies that the joule is a derived unit, which can be expressed in terms of base units, kilograms, meters, and seconds. Now here's the thing. Work is a scalar quantity and can be positive, negative, or zero. Work is a signed scalar quantity and can be positive, negative, or zero. So the question I have for you is, when is work positive and when is work negative? If you look at our previous lesson, I said the work done on a system is positive if energy is transferred from the object into the system. But work done is negative if energy is transferred from the system to the surroundings. But that is the conceptual meaning of positive and negative work No work simply means no energy leaves or enters the system. But in terms of the definition of work, what does that mean? So let's look at this definition with a critical eye. By definition, work is equal to F delta X cosine theta. This is the definition of work. Let's suppose that the object moves in the same direction of the force. Like in this case, somebody is pushing boxes forward and exerting a force forward. You can clearly see that this is the direction of displacement, delta X, and this is the direction of force. This means that theta is equal to 0. If theta is equal to 0, it implies that cosine of theta is equal to 1. In which case, the work done is just going to be equal to Fx multiplied by delta X, which is greater than 0. So what can we conclude in this case? When the displacement of the point of application of the force is in the same direction as the force, the work done is positive. Let me say it again in another words. When the displacement of the point of application of the force is in the same direction as the force, energy is transferred from the environment to the system, in which case the energy content of the system increases. Now, let's look at the case B, in which you have this is the direction of the displacement of the object, but this is the direction of force. You see that the angle is perpendicular. In this case, theta is equal to 90 degrees. Look carefully. In this particular case, there is a force and there is a displacement. So the question is, will there be work done? The cosine of 90 degrees is 0. If the cosine of 90 degrees is 0, it means that the work done, which is F delta X cosine theta, this will be 0. In other words, no work is done. Even though there is a force and there is a displacement. So this solidifies the fact that energy can only be transferred into or out of the system only if the displacement of the point of application of the force is along the line of action of the force. In this case, the line of action of the force is upwards. The displacement of the force, the point of application, is horizontal. So the angle is right angles, which means that no work is done. What about this case scenario in which there is a force, but there is no displacement? He pushes on a very large stone. Even though he exerts a force, delta X is equal to 0. If delta X is equal to 0, W, which is Fx, delta X will be equal to 0. In this case, no work is done. No work is done. So we can definitely conclude that work is only done if there is motion. If there is no motion, then there is no work. Motion of what? The point of application of the force. It's possible that I can exert a force, the point of application of the force moves, but the system as a whole doesn't. Typical example, if you hold a balloon that has been inflated and you compress the balloon itself doesn't move. It just compresses, but energy is transferred into the balloon and stored in the balloon as elastic potential energy. You can quickly see that because if you let go, the balloon does what? Expands. A similar thing occurs with a spring. You can compress a spring, but the spring itself will not move. The point of application moves. Understand the difference. The point of application moves. The energy is stored in the spring as elastic potential energy. So it's crucial that you remember that. Now, the last thing before I go is the fact that when you look at, if you draw a graph, this is x, the displacement in meters, and this is the force in newtons, you will recognize that the area bounded by this graph represents the work done by the force. Remember, the area bounded by this graph is equal to the force multiplied by delta x. This is x initial, this is x final. So this distance from here is delta x. The area is just length times width, and the length is the displacement, the width is really the force. So the area bounded by this graph is simply the work done by the force. In other words, the work done by the force on the system is simply the area under the force versus position graph as indicated by the shaded area. Now, if you have any questions, please, regarding what we have discussed, I will appreciate it if you ask in the discussion forum below. Thank you and remain wonderfully blessed. Bye-bye.
Manhattan, Brooklyn.